Okay, think about all the hidden brains around us. You know, your smart speaker, your car's computer, even that fancy new thermostat.
Hmm.
Embedded devices are everywhere, right? And while they all do wildly different things, it turns out they share some, well, surprisingly similar security vulnerabilities deep down in the silicon.
That's absolutely right. Whether it's some low power sensor or a high performance industrial controller, these systems often have fundamental weaknesses
Hmm.
right at the hardware level.
Yeah.
And today we're doing a deep dive into a pretty fascinating area for understanding those weaknesses, fault
Mm.
injection techniques, and also the clever ways engineers try to, defend against them.
Okay, so a listener actually pointed us to some really compelling stuff, excerpts from the Hardware Hacking Handbook. And honestly,
Ah,
it reads a bit like a spy manual for the digital age,
it kind of does, yeah.
detailing how to intentionally mess with hardware in, well, not unexpected ways.
And our mission today, really, is to pull out the core knowledge from those excerpts for you. We want to give you a clear picture of how attackers can deliberately introduce errors into a device's physical components.
To bypass security?
Exactly, to
Yep.
bypass its security safeguards. And, just as importantly, what measures are put in place to resist these kinds of sophisticated attacks.
Right.
Consider this your shortcut to grasping a pretty complex field, and a crucial one.
Fault injection. I mean, it sounds almost counterintuitive, doesn't it? Like breaking something on purpose to understand it better.
Uh-huh.
But in the security world, it's clearly more than just, random chaos, right?
Exactly. At its heart, fault injection is about pushing a device's hardware outside its normal operating conditions, but crucially in a controlled way.
Okay.
The goal for an attacker is often to circumvent established security. Think of it like trying to um, pick the lock of the hardware itself.
Right, right.
This could mean gaining higher levels of access than they should have, privilege escalation, or even extracting secret information like encryption keys.
And one way to do that, according to the book, is by messing with the device's internal clock, its heartbeat, basically.
Yes, clock fault injection is a prime example. By subtly altering the precise timing of that clock signal, the one that synchronizes all the operations within a device, an attacker can, potentially, induce errors.
Errors in calculations,
Yeah.
or...
Yeah, or in the sequence of its instructions.
So it's like giving the processor a sudden stutter. What kind of trouble can that actually cause?
Well, one really interesting consequence is something called metastability.
Metastability. Okay.
Imagine a digital switch getting confused, like it's not quite on and not quite off.
Yeah.
Its output becomes unpredictable for just a tiny fraction of a second.
Hmm.
Now, even that fleeting uncertainty can be enough to cause a processor to maybe skip a critical security check or, make a wrong decision somewhere down the line.
Wow.
It's like a single drop stitch kind of unraveling a whole piece of fabric.
That sounds incredibly delicate. How do you even achieve that level of, like, timing control?
Well, the book highlights field programmable gate arrays, FPGAs, as a key tool here.
FPGAs, right?
Think of an FPGA as a sort of reconfigurable silicon canvas. They allow for generating highly precise clock glitches by manipulating the clock's phase, essentially, making incredibly fine adjustments to when the clock signal rises and falls.
That's fascinating. But I'm guessing you can't just do this with any old off-the-shelf equipment. It's sound specialized.
You're right. The book really emphasizes that. Clock fault injection usually requires specialized hardware that's capable of that very, very precise control over the timing signals.
Okay.
And when you're trying to fine-tune this type of attack, there are two main knobs you're essentially turning.
Yeah.
The glitch delay, that's when the disruption to the clock starts, and the glitch length, how long that disruption actually lasts.
Okay, so that's manipulating time. What about power? I remember the material mentioning voltage as another key target.
Absolutely. Voltage fault injection is another powerful technique in the hardware hacker's arsenal.
Hmm.
Instead of playing with the clock, here the attacker deliberately interferes with the electrical power being supplied to the device.
So are you overloading it or
Right.
or starving it of power for a split second? What's the idea?
It's more often about creating a very brief dip in voltage, a glitch in the power supply.
Ah.
This sudden drop can cause the delicate logic circuits inside the chip to malfunction, potentially introducing errors into their operations.
The book talked about a crowbar technique. That sounds pretty dramatic.
It can be, yeah. The crowbar technique basically involves using a MOSFET, that's a type of tiny electronic switch, to essentially create a temporary short circuit right across the power supply.
Wow.
This forces a very rapid and significant drop in the voltage, Think of it like suddenly putting a massive drain on the battery just for an instant.
And I'm guessing the physical setup matters a lot too, like the length of the wires you're using.
Critically important, yes. The excerpts really underscore the importance of wire length in voltage glitching. Shorter wires minimize inductance.
Inductance. Right, the
Right.
resistance to current change.
Exactly. So by keeping the wires as short as possible, attackers can get much finer control over the shape and duration, the pulse width of that voltage glitch. It's a subtle physical thing, but it has a huge impact on whether the attack works.
And mux glitching was another term that came up in there.
Mux glitching, right. That's another way to achieve voltage fault injection. It involves rapidly switching between different voltage levels using multiplexer chips.
Okay.
Imagine quickly flipping a light switch back and forth, but you're doing it with voltage levels really fast. By precisely timing these rapid voltage changes, attackers can again try to induce those critical errors in the device's logic.
Mm-hmm.
And the book gives an example, actually, of how carefully tweaking the voltage and the timing of these glitches can even trick a device into skipping its own checks for valid software.
You mean like the firmware signature verification?
Exactly. That's a key security mechanism we should probably talk about more later. But yeah, you could potentially bypass it.
This is fascinating stuff. A
Yes.
little unnerving, maybe.
It can be.
Messing with clocks, messing with power. What else is in the hardware hacker's toolkit? Are we talking some kind of invisible ray next?
You're actually not far off. The next technique to consider is electromagnetic fault injection, or EMFI.
EMFI. Okay.
This involves using a focused burst of electromagnetic energy, a pulse, to induce faults in the target device.
Electromagnetic. Okay, so how does that actually cause a problem inside the chip? It sounds a bit like science fiction.
Well, it relies on Faraday's law of induction,
Oh,
basically.
physics.
Right. Remember that a changing magnetic field passing through a loop of wire creates an electrical voltage in that wire.
Yeah, vaguely.
Okay, well, inside an integrated circuit, there are microscopic loops of conductive pathways, tiny wires, essentially.
Right.
When a strong, rapidly changing magnetic field passes through these tiny loops, it can induce a voltage difference. And that voltage difference can potentially cause a bit of data to flip change a 0 to a 1 or maybe a 1 to a 0.
Okay, so what's the big advantage of using electromagnetic pulses then? Why not just stick to, physically connecting wires?
Well, a significant advantage that the book points out is that EMFI often doesn't require any direct physical connection to the target device,
Yeah.
at least not initially. You might not need to go through the often complex and, frankly, potentially destructive process of decapsulation.
Yeah, removing the chip's packaging.
Right, removing the chip's protective packaging. You might not need to do that right away with EMFI, so it can be a less invasive initial attack vector.
That sounds much more subtle. But how do you aim an electromagnetic pulse at, like, a tiny part of a chip? Seems hard.
The book explains that EMFI can actually be quite localized. You use a carefully designed and positioned probe, which is essentially just a small coil of wire.
Okay.
You place it directly over the specific area of the chip you want to influence. The closer and more precisely you align the probe, the more targeted the effect becomes.
It still sounds a bit risky, maybe, for the attacker. Are there hazards involved?
Oh, there definitely are. The excerpts caution that EMFI often involves working with high voltages and high currents to generate those strong electromagnetic pulses. So safety precautions were absolutely crucial.
Good to know.
The book also briefly mentions a more specialized use, using continuous electromagnetic fields, not pulses, to subtly influence the behavior of, say, random number generators within a chip, potentially making them less random.
Interesting.
And, for the truly DIY enthusiast, the book even touches on how you might build your own EM probe using coaxial cable, though it also mentions you'd need a low-noise amplifier to boost the signal enough for it to be effective.
Okay, so we've covered time, power, and magnetic fields. Is there one more sort of exotic method we haven't touched on? Something involving light, maybe?
You've absolutely nailed it. Optical fault injection is another sophisticated technique, and it involves using highly focused lasers to target very specific microscopic areas on a chip.
Lasers on a microchip. That sounds incredibly precise, but I think the book mentioned that tricky decapsulation step again, didn't it?
Yes, optical fault injection almost always requires decapsulation. Has to.
Right.
Because the laser needs a clear, unobstructed path right down to the silicon die at the heart of the chip. So the protective packaging typically has to be chemically removed, usually with acid.
Acid. Yeah, that sounds tricky.
And the book notes, yeah, this is a delicate procedure, potentially hazardous. Requires specialized skills, special equipment, not something you just try at home.
And what kind of laser do you even use for something like this? It can't be just your standard laser pointer, I assume.
No, definitely not. The book explains that targeting silicon with light actually presents a unique challenge.
Hmm.
You need a laser wavelength that can penetrate the silicon material itself,
Okay.
but also be absorbed by the even tinier structures within it, like the transistor's gates, which are also made of silicon. It's tricky.
So there's a sweet spot.
Exactly. There's a sweet spot, they say,
Yeah.
often a wavelength where silicon transitions from being opaque to being more transparent. The book mentions 164 nanometer infrared lasers as a common choice.
Mm-hmm.
And it also points out that techniques like thinning down the silicon substrate, making the chip physically thinner, and polishing its surface can further improve the accuracy and effectiveness of this laser targeting.
So with all these incredibly intricate ways to inject faults manipulating clocks, voltage, EM fields, even lighten, what are attackers actually hoping to achieve? What are the high value targets inside these devices?
Yeah, good question. The book emphasizes that attackers are typically going after the security mechanisms, the things designed to protect the device.
Like what?
Oh, anything from, say, the secret password that controls access for debugging, JTAG passwords, things like that,
Okay.
to the digital signatures that verify the software hasn't been tampered with, or even sensitive cryptographic keys that are meant to be locked away, totally inaccessible to software.
And how does introducing just a tiny fault help you bypass something like a password or a digital signature? It seems like a leap.
Well, let's take firmware signature verification as an example. Many modern devices, before they run their main software, they check if it has a valid digital signature from the manufacturer, right?
Right. To stop you loading bad code.
Exactly, to prevent malicious code from executing. Now, ultimately, this whole verification process boils down to a simple decision.
Mm-hmm.
Yes, the signature is valid, so boot the software. Or, no, it's invalid, so halt.
Okay.
Deep down in the boot software, this decision often comes down to a single conditional jump instruction in the code, like an if this, then go here instruction.
Mm-hmm.
A very precisely timed fault, introduced just as that specific instruction is being executed, can effectively flip the outcome of that decision.
No way.
Yeah, it can trick the device into thinking the invalid, unsigned firmware is actually legitimate, and then it just boots it anyway.
Wow. The book even had that example about hacking a toothbrush. That sounded almost unbelievable.
It does sound a bit wild, doesn't it? But it's a great illustration of the potential. The example basically outlined a complete attack. First, finding some vulnerability that let them extract a crypto key.
Okay.
Then reverse engineering the toothbrush's firmware, modifying it to include a backdoor, like some hidden command,
Right.
and then using voltage fault injection to bypass the firmware signature check and get their tampered code running on the toothbrush.
On a toothbrush. Amazing.
It really shows how these seemingly abstract techniques can be used in a very practical way, even on a somewhat, mundane device.
Mm-hmm.
And the book also introduces this idea of fault sensitivity analysis, essentially trying to map out which specific parts of a device are most likely to exhibit exploitable behavior when you hit them with a fault.
Like finding the pressure points?
Exactly, finding the pressure points in the hardware.
It definitely sounds like getting these fault injection attacks to actually work in practice is a very refined process. It's not just randomly poking at things, is it?
Absolutely not. The book really stresses the highly iterative nature of fault injection. It often requires a significant amount of careful experimentation, lots of tuning of various parameters.
Right.
We're talking about the exact timing and duration of a clock or voltage glitch, the precise strength and timing of an EM pulse, or the power level and focus of a laser beam. It's a real process of subtle manipulation and very careful observation.
So you're not just like blasting things with energy and hoping for the best?
Not at all, no. The excerpts describe using a dedicated fault injection test bench, often controlled by a PC.
To automate it.
Yeah, exactly, to automate many of these attempts. This lets researchers, or attackers, systematically try a huge range of parameter values and then meticulously observe how the target device responds each time.
And what kind of responses are they looking for besides the obvious, yay, I bypassed the security?
Well, a successful bypass is definitely the ultimate goal, but even other outcomes can be valuable.
Like what?
They might see the device throw unexpected errors, maybe crash completely and become unresponsive, which might indicate you're close. Or even, in some interesting cases, maybe leak sensitive data from its memory in some unexpected way, just spit something out it shouldn't. The book emphasizes that even seemingly random or unintended effects from a fault can sometimes be carefully analyzed and ultimately exploited to gain some kind of advantage.
This all paints a pretty concerning picture, though, for the security of our devices. Are there any defenses against these kinds of sophisticated attacks? Or is
Yeah.
it just game over?
That's the crucial question, isn't it?
Yeah.
The book points out that, generally speaking, standard general-purpose hardware isn't typically designed with strong defenses against malicious fault injection specifically in mind.
Oh, okay.
Secure microcontrollers, the ones you find in smart cards, some critical security modules, those are notable exceptions. They often do incorporate specific hardening measures.
Right.
But that said, there are countermeasures that can be implemented in more general hardware to make fault injection attacks significantly more challenging.
Okay, so what kind of defensive measures are we talking about?
Well, the excerpts outline several examples. You can have fault detectors built into the hardware, things that continuously monitor, say, the supply voltage and the clock frequency.
And sound an alarm if something weird happens.
Exactly. Trigger alarms or resets if any unusual deviations are detected. Then there's redundant execution.
Doing calculations twice?
Yeah, performing critical computations multiple times and comparing the results. That can help identify if a fault has introduced an error.
Makes sense.
You can design secure state machines to be less susceptible to transient errors. Timing randomization can introduce unpredictability, making it much harder for an attacker to precisely time their fault injection attempts.
Ah.
And various masking techniques can be used to sort of hide sensitive data while it's being processed, making it less vulnerable to being exposed by a fault.
But even with all these countermeasures, can a device ever be truly, immune to fault injection?
That's the ongoing challenge. The book highlights that. Evaluating the effectiveness of these countermeasures is tough.
Why is that?
Well, sometimes even really well-intentioned protections can be inadvertently weakened or even completely removed by things like compilers or synthesis
Oh,
tools.
during the process of making the actual chip.
Exactly. During the process of turning the high-level design into the low-level instructions the hardware actually executes, something can get optimized away without realizing the security implication.
Mm-hmm.
The excerpts also briefly mention industry security certifications like Common Criteria and JIL. These include evaluations of a device's resistance to both fault injection and related side channel attacks. So they provide a benchmark.
But it's an evolving field.
It is. The security landscape is constantly evolving.
So, okay, to sort of bring it all together then, we've taken a pretty deep dive into this world of hardware fault injection today.
Indeed. We've explored the main techniques attackers use to introduce these intentional errors: messing with the clock signal, disrupting the power supply voltage, using electromagnetic pulses, and even targeting with lasers.
And the ultimate goal for an attacker, really, is to very precisely induce these faults in just the right way, at just the right time, to allow them to bypass the device's built-in security mechanism.
Exactly right. And understanding these techniques is becoming so important, not just for those on the offensive side of security research, the hackers, but also critically for the engineers who are designing the next generation of more robust and secure embedded systems. It's crucial for defense, too.
This has been incredibly eye-opening, seriously. It really makes you think about the hidden vulnerabilities that might be lurking inside all the technology we rely on every single day.
It really does. And it kind of leads to a final thought for you, the listener, to maybe mull over. Given these relentless advancements we see in both the capabilities of our hardware and the sophistication of attack methods, how can we really ensure the long-term security and trustworthiness of our increasingly interconnected and deeply embedded world?
Yeah.
You'll consider that constant balancing act
Yeah.
between security, the cost of implementing that security, and the desired functionality in the design of all these devices.
It's a huge challenge.
It is. And if you are eager to explore this fascinating field further, the Hardware Hacking Handbook, especially the chapters we've sort of touched on, and also the work of pioneers in the field, like Colin O'Flynn and Joe Grand, those are excellent resources for continuing your own deep dive.